In section 1 of chapter 6, we are going to be applying what we did in chapter 5, which was algebraically manipulating and identifying certain things in rational expressions and rational equations. Now, we're going to make it y equals, and we're going to be graphing these things. Now, the difficulty of this chapter is largely dependent upon how confident and comfortable you are with the previous chapter. If you were confident going, oh yeah, I know how to factor, oh yeah, I know how to simplify rational expressions, this should be a cakewalk. If you're struggling with it, good news, you get to review some more. All right, so here's what we know thus far. This is what we did in the past. These are two rational equations. Normally in the last chapter they were expressions, meaning I didn't have f of x equals. I just had the part 1 over x plus 2. What I'm hoping you recall is that for problem number 1, you can't really do anything with it. It's not factorable, it's not simplifiable. But the one thing we could do is list the discontinuity that x cannot be equal to negative 2. The reason x cannot be equal to negative 2 is if x was equal to negative 2, you'd get negative 2 plus 2, which is 0. The denominator would be 0, and that breaks one of the two fundamental rules in mathematics that you know thus far. You cannot square root negatives, which we're going to kind of remedy this year. And this is the one that we're not going to remedy this year. You're going to have to take calculus to figure this out. You cannot divide by 0. You cannot take a thing and break it into 0 pieces without not having that thing anymore. Division does not take away. It breaks into pieces. That's kind of like saying a pizza with 5 slices in it is divided by 5. A pizza with 1 slice is just the pizza and you don't do any cuts. It's the full pizza. A pizza with 0 slices is not mathematically or logically possible. That's me saying I want a pizza with no pizza.
What happens after you eat pizza?
Then you don't have a pizza anymore. So you still don't have a pizza. This is dividing by 0 saying I want a pizza with no pizza. So mathematically, we cannot do it. Calculus kind of broaches that topic. Problem number 2, same thing, except now it's factored. There are 2 parts of the denominator, an x minus 1 and an x minus 4. If this turned into 0, doesn't matter what this term is. If it's 0 times 13, it's still 0. If it's 0 times negative 261, it's still 0. We are looking for when either of these is 0. So that would be when x cannot be equal to 1 or positive 4. Because if it's equal to either of those, you would divide by 0. As a little special note, you might also notice the x minus 1 on top and bottom would eliminate. That's when things get really crazy, because then you get 0 divided by 0, and that's even more confusing. Which again, you will broach in calculus.
0 divided by 0, 1.
What we're going to be doing now is we're going to be talking about the discontinuities. We're going to be talking about how these interact with the graphs. This is going to be slightly challenging. I'm just going to let you know. And the most annoying part about this chapter is I'm going to show you how to represent rational equations graphically. I do not have, or I can't give you all the tools to accurately graph them. I can give you some of the key characteristics, but you will not understand how to completely graph them until, and this is kind of a trend in this lesson, until you take calculus. Calculus completes the puzzle that I'm setting up now. So we're kind of only going halfway through the topic, but we're covering the main beats. Calculus just kind of does the last smoothing out of the edges. So for problem number 1, I have f of x equals 1 over x plus 2. I know that x cannot equal negative 2. That is called a discontinuity. Before I even start to graph this, I want to write that. You will not, but I want to make sure that we write it on our notes so that you understand what this means once we get to the graphs. Discontinuity. It's a discontinuity. All right, so what does this look like? This is going to look like this. Negative 2. It's going to start super flat, super flat, super flat, super flat, and then it's going to start curving. Then it's going to curve. and it's going to curve, and it's going to curve, and it's going to curve, and go down faster and faster and faster and faster. This is where the weird thing happens with this graph, because it's going to go down. As we're going from left to right, it's going to keep going down forever and ever and ever. It's going to approach negative infinity. It does not exist at -2. We've already established that algebraically. We already understand why that does not occur. Here's where the weird part comes in. Here's the next part of the graph. Somehow pops up top. Let me reiterate why this is weird. If you look at it like a book, reading it from left to right, it starts flat. That's fine. Things start flat when they're fractions. And then it goes down faster and faster and faster and faster and faster and faster. And then at some point where it's discontinuous, pops to the other side. Now it's up at infinity. We've already discussed this, but I want to show you graphically what we just created. We created an asymptote. And now I get to go to the vocabulary because we did not use the word discontinuity. I didn't highlight that and point at it for no apparent reason. I want you to understand why we use the word discontinuous and discontinuity. Most functions that we have dealt with and that you have dealt with in your life are called continuous. Here's the layman fancy way of understanding what continuous means. It means you can graph the function without ever lifting your pencil. You can graph it in a continuous line. You never have to lift your pencil. Quadratics, parabolas, are continuous. Absolute values, they have a sharp corner, but they're continuous. Cubics, continuous. Exponentials, continuous. This is the first function that is discontinuous. If I want to graph this at that asymptote, I have to lift my pencil. That's why it's called a point of discontinuity, because it is the location, the point, where the function ceases to be continuous. It's discontinuous. Now that said, now I'm going to do number 2. I'm going to erase this one so I can. Problem number 2 is different. Problem number 2 looks similar. In fact, if you graphed it on a graphing calculator or even on Desmos, problem 1 and 2 are going to look similar, but there's a very, very critical key idea that I want to get across. So, problem number 2, if I wanted to graph it, it would look like the following. It is going to start. Give me a sec. It's going to look like this, roughly. I'm doing a general sketch, so sue me. All right. So we're approaching 1, we're approaching 1, we're approaching 1. Mr. Silva, you need to turn more. You need to turn more. Nah.
So that goes to 4.
Here's the weird thing that makes these complicated. Problem 2, I have two discontinuities. I have x equals 1 and x equals 4. I respected one of them. I respected the 4 and let it have a vertical asymptote. But I ignored the discontinuity of 1. I didn't ignore it, I just haven't finished it yet. Because those two discontinuities are different. Because if you recall back when I started this problem, I said x minus 1s would eliminate. The discontinuity that comes from it is labeled differently and also shows up differently on a graph. This one is actually referred to as a removable discontinuity, which I'll abbreviate as disc. The other one is called we're fairly basic in this, non-removable. Why is it called non-removable? Because I didn't remove it when I simplified the problem. There are 2 types of discontinuities for rational equations: removables and non-removables. Non-removables are very evident when you look at them graphically. There's a vertical asymptote. The equation splits. Removables are a little bit more tricky. Because in this instance, you have x minus 1 divided by x minus 1. They eliminate. Meaning the part where you would have a discontinuity eliminates out of the problem once you simplify it. What that does graphically is at x equals 1, that's the removable discontinuity in this problem. At x equals 1, the function does not exist here. It doesn't exist there. It is an open dot. The reason I wanted to show that to you later is because if you use any technology, it will not show that. Because if you think about this from a technology standpoint, it's like they're drawing or they're graphing the line, and then it's just one location it doesn't exist, it just skips one pixel. But because that's such a small region, and also because the way that monitors and visual technology works, it grounds the colors of the pixels around it, it never shows up. You have to be able to recognize that it exists and show me graphically, because technology won't fill that in. This is one thing that I do want to illustrate. For removable discontinuities, you on your graphs have to show me it exists. It will not show you using any of the technology that you have. Because if I wanted to graph that problem on Desmos, this is what it looks like on Desmos. If I pop that equation into Desmos and I graph it, notice two things. One, it does not actually show the vertical asymptote at 4. It doesn't actually draw the vertical dotted line. I do require that you do that. But two, at x equals 1, which is right here, at that location, nothing looks out of the ordinary. Technology will trick you if you don't catch this. However, Desmos is the closest to doing this correctly, because if you go to your mouse and you click on it, it actually will put in an empty dot at that location if you hover over it. It's just that if you look at it just from the general graph after you hit enter, plugging in Desmos, it does not show anything right here. But as soon as you put your mouse on it and click it, it'll go like, oh yeah, it doesn't exist there. So I just want to make sure that's clear, because this is a topic that does confuse students. I want to make sure that we're clear on that. Both discontinuities are showcased. It's just technology doesn't typically show the open dot, but on your graphs you will have to. So what I just did is a prelude to what you are going to be doing. You are going to be graphing, just not in this lesson. This lesson, all I'm asking you to do is to identify the two types of discontinuities from a problem. I'm not asking you to graph it. I will in the future. I am not in this lesson. So for problem number 1, the discontinuities are, well, this would be a discontinuity at x equals 0. This one is at x equals -3, and this one is at x equals 4. So those are my 3 discontinuities. X cannot equal 0, -3, or +4. Those are my discontinuities. That's what we did in the previous chapter. What we're doing in this chapter is we're labeling them as one of the two. They are either removable, which I just abbreviate as rem, or they're non-removable, non-rem. You just need to categorize them. Problem 1's pretty straightforward because I have an x plus 3 on top and bottom. So the discontinuity that came from that portion, that got removed, so it's going into the removable category. The other two, the 0 and the 4, they did not get removed. So they go in the non-removable category. And these are my answers. Now, before I answer any questions, I do want to illustrate, because some students like to ask, what about this x minus 1, Mr. Silva, what does it do? We'll go over that later. That does something else on the graph. We are not focusing on it right now. We are just focusing on the denominator. The numerator we will focus on later. Problem number 2, a little bit tricky. I'm sure you guys could have seen this a mile away by now. How is this problem tricky? It's not factored for me yet. I gotta factor it first. So, the function delta, oops, wrong color. Function delta of x will be equal to the numerator of an x cubed plus 11x squared plus 30x. They are all divisible by x, so I'm going to factor out an x. Leaving with x squared plus 11x plus 30. Denominator, GCF. All 3 terms are divisible by 3. And they all have an x in common. So that'll leave me with x squared plus 4x minus 12. Then I look at those parts inside the parentheses and I factor them. Use whatever technique you want. This is going to be delta of x is equal to x times something, multiply to 30, but add to 11. That's 5 and 6. So it's x plus 5 and x plus 6. Now's when I activate my cheat codes a little bit. We're doing rational equations. Rational equations typically have things eliminate on top and bottom. That means I'm willing to bet that when I factor x squared plus 4x minus 12, I'm willing to bet that either x plus 5 or x plus 6, one of them is going to show up down here. So I'm thinking x plus 6 and x minus 2. Now I'm going to jump straight to the answer. I'm going to skip the part where I list the discontinuities. I'm just going to go straight to labeling them as removable and non-removable. So I'm looking for the removable discontinuities and the non-removable discontinuities. Because if I simplify this, the x and x would eliminate, meaning x equals 0 is a removable discontinuity. And then I have an x plus 6 and x plus 6 eliminate, meaning that it is also going to give me a removable. And the only one that did not get removed from the denominator is the x minus 2. So its discontinuity, which is positive 2, is non-removable. Now the last thing I want to iterate before I leave you is there is some more vocabulary of sorts. I just want you to be able to recognize it. I will put it in the instructions. But removable and non-removable are the terms I like to use because it hints at what you're going to be doing, either removing or not removing. They do have other names. Removable and non-removable is also referred to, or non-removable is also referred to as a point of discontinuity. Because if you think about the graph where it was an open dot, it's an open point. So non-removable points of discontinuity, they're called vertical asymptotes. Just as an FYI. Sometimes I'll refer to them as vertical asymptotes. Sometimes I'll refer to the removables as point discontinuities. Just be prepared for both. I typically like sticking with this vocabulary, removable and non-removable.